Okay guys, back at it again with another video. I'm going to do this structure just like the last one where I go over the chapter and then I'll go through the practice homework or quiz, whichever it is. Okay, so you guys are doing chapter 8 now, which is elimination reactions. And so, oop. I'm going to put my phone on Do Not Disturb. Okay. So, one of the biggest things you're going to be working with is alkenes. That's what this whole chapter is going to be because it's E2, so we're breaking that double bond. Forming a double bond, sorry. Didn't mean to say breaking. That's addition. You'll do addition in chapter 10, I think. Anyway, so you're going to be working with alkenes. So we should probably just cover the stability of them first. So we've got a mono substituted. And that just means like the carbon of the double bond, is only connected to one. Oh, I'm big. That's crazy. A sonic email rolling through on this video is crazy. Anyway, so the carbon in the double bond is only connected to one other carbon, right? That's why it's mono substituted. Then we'll have bi substituted or di. Not really sure which one it is. I think it's di. Di substituted. Sounds better. Anyways, I'll write it as di. And then again, so this carbon in the double bond is connected to one carbon over here, but then this one is also connected to another carbon. 1 plus 1 equals 2. Di substituted. And these ones can either be cis or trans. So this is a di substituted, but this one is cis, right? They can also look like this. And then this one would be trans. All right. And then we have tri-substituted, which would look something like this. And I'm going in order of like increasing stability. All right, so this one, carbon in the double bond, this one's connected to one here, and then also connected to one here. This carbon in the double bond is connected to one, right? So we've got a total of 3, which is the tri. And then the most stable you can get is tetras substituted. And when we look at this, the 2 carbons in the double bond are both connected to 2. Right? That's where the tetra's from. And so when we look at these, it is increasing in stability this way. All right. Now we'll just get into our reactions. So we've got E1 and E2, just like we had SN1, SN2. So E1. Very similar to SN1. It's going to be a first order rate law. and the rate is just like an SN2. You got your rate constant, and then we only worry about the alkyl halide because it's going to be a multi-step reaction. Excuse me. Excuse me. It prefers weak bases. So I know in our substitution reactions are called nucleophiles, right? We kind of judge the strength of the nucleophile based on its basicity. This is just genuine. We're using bases. So it likes weak bases. Emphasis on the weak. And polar protic solvents. Again, pretty much just like SN2. So what do we say about protic solvents? Remember, they can hydrogen bond. We'll go over, yeah, that's fine. We'll just leave it there for now. So we'll do an example of an E2 reaction. Ugh, I keep doing that. Okay. So let's say we have carbon, CH3, 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 chlorine. Also, this is very similar in the sense that it's going to be like secondary, tertiary are going to move the fastest on E1. E2 is a little bit different in that, honestly, anything primary, secondary, or tertiary could do E2. But for E1s, because it's going to have that intermediate, a secondary or tertiary because it's more stable, those are going to be something that you see reacting better for E1 reactions. The main thing to pay attention to when you're trying to distinguish is going to be the strength of the base, and we'll go over strong bases later, but the strength of the base is going to be the biggest thing. And most of the time it gives you, so like it'd be 80% ethyl alcohol, and then like 20% water. And this lets you know it's a weak base because it's diluted, right? We're diluting it with water. And then our heat will be 25 degrees Celsius. And this is just an old example I have from my notes. And then you're going to end up with carbon, double bonded to carbon. This has a CH3, CH3, H, H. Okay, so let's get into a reaction mechanism. And this one, yeah, okay. Very, very similar to SN2. We're going to start with our compound, right? Our CH3, methyl, bonded to our chlorine, right? Okay. So when we're labeling these compounds, the alpha carbon is going to be the carbon that the substituents are attached to, right? And then beta carbons are going to be the ones that can like be reacted to. So like this is a beta carbon. This is a beta carbon. And this one's a beta carbon, right? And so you'll just determine, we'll go over things that we're looking at to determine which one is going to be the one that we use. A lot goes into it, like steric hindrance and things like that. Less so with E1, just because, everything happens in a multiple step reaction, versus E2 would be all in one. So our first thing, our chlorine's going to leave. It's our leaving group. I don't like that. Chlorine pops off. And we're left with a cation, carbocation. The carbon's positive, it's lost a bond. Chlorine took all the electrons with it. So now I'm going to restructure how we're looking at this, right? So keep in mind that this has 3, right? We've got, oh, why isn't this showing? My laser's not working. Okay, well, so just keep in mind that we've got 3 methyls, right? So I'm just going to restructure the way that this molecule is going to look. So we've got carbon, carbon, H, 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 and then CH3, right? So these are all of our beta carbons. And I'm only restructuring it like this, so that way you guys can see the hydrogen a little bit better, because the hydrogen is what causes the double bond, right? The beta carbon's hydrogen. So all of these are beta carbons. You could have used any of them, really. There's no rhyme or reason behind why I chose the one that I chose, and you can't even tell which one I chose because I just restructured the molecule, right? It could have been any of them. But they're all beta carbons, and they're all pretty equivalent beta carbons. So we look at the hydrogen, right? One of the hydrogens attached to the beta carbon. So what happens is this hydrogen is going to jump into this bond, or the electrons in this bond are going to jump in there, right? Why? Because we'll have water, and this oxygen is going to steal this hydrogen. So in this case, our water was the base, right? The ethyl alcohol also is a source of base, but it's kind of, you get into solvents that you guys have. So these compounds get like put into a solvent or a liquid to dissolve and to do the reaction inside the little test tube. So that's another thing to look at. If you don't know if it's a base or not, it could also just be the solvent in your reaction. So water's going to come in here. The lone pairs on the oxygen are going to take a hydrogen off the beta carbon. And the electrons from the hydrogen bond are going to jump in between the beta carbon and the alpha carbon. And that's what's going to form our double bond. So now this carbon is double bonded to that one. This one only has the 2 hydrogens, CH3, CH3, right? And so this is the exact same thing up here. I just broke it down into the reaction mechanism, but you see how this was our starting material. This is our starting material. I didn't talk about the ethyl alcohol, and that's because it's just the solvent. The water is the base that I was using in this one. And then we ended up with the same product, right? 2 hydrogens. This carbon has 2 methyls. I wrote it backwards, but they're the same. So identifying the alpha carbon and the beta carbon is going to be the most important thing. The alpha carbon, here, I'll make note of that. Alpha carbon has the leaving group attached to it. AKA alkyl halide. I don't think you guys will have reactions that aren't alkyl halides. Or the whole thing's alkyl halide, so really it's just AKA the halide itself. So if you notice, this is the alpha carbon, right? Because it's connected to the leaving group. Okay? Beta carbons are just carbons attached to the alpha carbon. Can write that too. All right. So this is an E1 mechanism. Everything's about the hydrogen being ripped off, and then, you're going to have a byproduct of H3O+, but shouldn't be too worried about that. I don't think he really talks about that a whole lot. As far as the reaction goes, this is transition state 1, right? This is an actual step. This wasn't a real step. It was just me restructuring our molecule so we could see what was happening. This is transition state 2, right? Because something actually changed within the molecule. This one I was just reshaping it so we could see it a little bit better as far as the hydrogen goes. I don't think you guys get reaction coordinate diagrams of this one. I didn't include it in my notes, so let me see. This is chapter 8. That's for E2. I'm not seeing one for E1. Okay, cool. Don't see it. Anyways, if you want to go, and we can do that. We'll draw the transition states themselves. So we've got our carbon, our methyl group. What's going to have a dotted line, you think? Because remember, the dotted line represents a bond being broken or formed that wasn't there to begin with. If you said bond to chlorine, you were correct. If you didn't, maybe review that. So we've got chlorine. And so chlorine is going to become negative, right? So we're going to give it a partial negative. And this carbon is going to become positive. So we're going to give it a partial positive. Close it in our brackets. Give it the transition state symbol. And this is it. Then over here we've got carbon, or CH3, hydrogen. Okay, so this one is going to look wacky. We've got a line here, and then a line out to a hydrogen that was ripped off. Oops. And then this hydrogen eventually gets bonded to an oxygen from the water, right? So this is a really long transition state. This carbon, no, just the oxygen, yeah. So the oxygen is going to have a partial positive because it went from being neutral to positive in H3O+. I hope that these make sense. It's just another way of representing everything that's happening in the reaction mechanism. So this is transition state 2. Excuse me. All right. Let's move on to E2. E2 is kind of similar to SN2 in a lot of things. Like, it's second order. Right? So the rates are the same. Our rate's going to be our rate constant, our alkyl halide. But instead of nucleophile, it's listed as base. So if you get option choices, you'll get some on the test or your quiz. And when it talks about the rate, you'll have options for alkyl halide and nucleophile. And so it's really important that you identify whether it's SN2, EN2, like, is it a substitution reaction or an elimination reaction? Are we forming a double bond or are we just swapping atoms? That'll be the easiest thing to distinguish so you don't mess up those questions. They're supposed to be kind of easy gimme questions, but, you know, test brain gets ya. So E2 likes strong bases. Aprotic solvents. Meaning it cannot hydrogen bond. And it requires an antiparaplanar hydrogen. And I will go over what that means, because that's like the most confusing thing about it. And so you kind of look at it with chair structures. And that's one way that he shows that it's anti-paraplanar. And there might be like some versions or some chairs on the test or your quiz about it. So let's go over an E2 reaction. And we'll kind of walk through it in that sense. We'll just go through the mechanism because that's probably going to be the easiest way to see it. Okay. So we've got carbon, 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 hydrogen, 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 and then bromine. We'll do bromine. Hydrogen, hydrogen, hydrogen. Okay, so take a second, look at this. What's the alpha carbon? The one in the middle. What are the beta carbons? Or is there only one beta carbon? There's two. It's each carbon connected to the alpha. Okay. So we're going to mix it with a strong base. All right, so it's going to be listed like this on your exam, right? And you're going to look at this and be like, well, how do I know if this is a strong base? Well, we know that this is an ionic bond, so really this is an A+, and O-. The charge on the oxygen makes it a strong base, right? It's negatively charged, so it really wants a proton. It wants a hydrogen, so that way it can be a neutral charge. It doesn't like being negative charge. That's unstable. So negative charge, here, let's make it red so it pops out a little bit more. Negative charge is kind of a giveaway that it's a strong base. So oxygen really has these lone pairs now because it's not actually bonded to the sodium. Is Na sodium? Yeah. Okay, so everything is happening at once, right? Just like SN2. Meaning our leaving group, or a halide, pops off, right? And it's going to get a negative charge. And then oxygen is going to steal hydrogen from the beta carbon, and this is going to form a double bond down here. All right, it's all happening at once. And really, if you think about it, because this, is going to have its lone pairs now, this is going to bond here to the positive charge. So a lot of things happening at once. So then we end up with a carbon double bonded to a carbon. We've got 2 hydrogens because 1 hydrogen was stolen. And then hydrogen, and this one had a methyl. Right? And then our byproducts is going to be, our conjugate acid to the base because it's now stable. Oxygen got its hydrogen. And then, bromine ended up bonding with our sodium. So we got an NABR. These are just byproducts. Not really important. Just showing you guys because, in chemistry, you don't just destroy things, it went somewhere. So this is just kind of where everything else went. So we only have one transition state, right? That's what it means to be E2. It all happens simultaneously. So let's draw our transition state, right? We've got carbon, we've got CH3, hydrogen, and then because it was bonded to the bromine, but eventually it isn't, so we've got bromine down here, hydrogen, hydrogen that was stolen, and it then bonded to the oxygen on our base. Good Lord. We've got oxygen, CH2, CH3. So oxygen was negative, right? So it's going to have a partial negative till it picks up the hydrogen, then it won't be negative anymore. But we don't really need to include that. I don't see that in my notes. Okay, antiparaplanar. So we've got para, meaning it's on the opposite side, right? And anti because it's trans. I don't know, when you are not anti, but okay. Let me think of a good way to explain it. So it's staggered, right? It wants to be as far apart as possible because for this to happen simultaneously, that hydrogen needs to be far away from the bromine. Otherwise, there's steric hindrance, right? Because if it's close to the bromine, then as the bromine's popping off, the big base can't really get in there. So it needs to be as far away as possible so it's positioned on opposite sides of a single bond. And so if you see that here, we've got bromine down all the way over here. This is the farthest hydrogen possible from bromine. So we didn't use this one, we didn't use this, and we didn't use this for a reason. Because it's not antiparaplanar. And I'll show you guys my old notes with the chairs because that shows it a little bit better. But this is put our brackets around it. This is the transition state. So E2 is what's called regioselective, meaning, regio like region. So there's steric hindrance, so it can only take a certain hydrogen. That's what it means by regioselective. And it follows Zaitsev's rule, meaning the major product will be the more substituted, more stable alkene. We'll write that. I'm sure you guys have talked about it, but we'll just write it. These are going to be like definition questions, so it's important to know because he does ask things like this. Okay, and we talked about stability over here, right? So it's going to create the most stable, possibility. It doesn't want a mono-substituted, would not really prefer di-substituted. If possible, it's going to create the tri-substituted or tetra-substituted double bond. So that's also important as far as like with our beta carbons, finding the beta carbon that is their hydrogen on the beta carbon that is anti-paraplanar to our leaving group and is going to create the most stable alkene, which is going to be the most substituted. And there'll be examples on the practice quiz, I'm assuming, and we can work through those. Strong bases, because, we need strong base for E2. So you've got NaOH or KOH, NaOCH3, or like the one we just used, NaOCH2CH3, strong base, NaNH2, sodium nitrite. This is one I feel like I saw in the exam. Potassium tert-butyl oxide, I think is what it's called. And then DMSO is one. So these are strong bases. If you see one of these, it's most likely an E2 reaction. We'll go over. He will probably ask like a definition question on the type of halide it is. So if you've got multiple halides, geminal. Sorry if any of you guys are a Gemini. This is the way it's explained to me and to help me remember. Geminis are two-faced. So geminal is two-faced, meaning just the carbon itself has the two halides on it. Right? So this is geminal. There's two halides on the same carbon. Two-faced. And then you've got vicinal, which is, they're just neighbors. They're next door neighbors. You got an X here and an X here. It's not on the same carbon, but it's on the carbon adjacent. So they're next door neighbors. All right. And then you have a little bit of alkyne, right? Just move over here. You got stuff about alkynes in this chapter as well, which is just triple bonds, right? So terminal means the triple bond is outside. And then you've got internal, which you know kind of makes sense. Guess it's going to be inside. Okay, so internal, we'll draw examples of both. And then terminal. This is internal. This is terminal. It's on the inside, outside. Internal alkynes. So this is more about making alkynes. You guys aren't really breaking them right now. Internal alkynes are created when there is two equivalents of base used. Two equivalents of base. So it'll be like you'll have bromine, bromine. And right here in your reagents, it'll be like two equivalents of base. And then that's how you make the one I showed you up there. And you end up with triple bond. Right? Looks just like that. So this one is what? What kind of... Where did I write it? What kind of halide are we looking at over here? They're next door neighbors, right? So they're vicinal. But you can do the exact same reaction with them being geminal. You know, bromines are here. Two equivalents of base because they're on the inside. And when I say inside, I mean like there's carbons to both sides, right? That's why it's inside. It's not on the external side. It's not an external carbon where it's like there's nobody to the like next to it. There's carbons on both sides here. So then you end up with exact same thing. Really, this line is like through. I just feel like you see the triple bond a little bit better when I have it separated. And then terminal are treated a little bit differently. They are treated with three equivalents of base. And one equivalence of a dilute acid. So you end up with, we'll do it with both terminal and geminal again. Or geminal and vicinal. Sorry. So these two are next door neighbors. They're vicinal. You're going to treat it with two equivalents of base, one equivalence dilute acid. Okay, notice that this bromine is on the outside, right? Like this carbon is an external carbon. That's why once it gets a triple bond, it's just on the outside, like there's nothing connected to it. That's what makes it terminal. So the starting materials is what makes it terminal or internal. So this one doesn't have a ring, but it works the same. You see this carbon, like it's going to be bonded to this one right here, and it's on the outside. Three. And one equivalence. Dilute. What am I spelling? Acid. So then you end up with 3 here we had, and then triple bond. Let's carbon count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same number of carbons that we started with. So those are like the most important rules I had. Let's look at the antiparaplanar. I wish this, oh, it's working now. Cool. Okay. So, E2 follows, yeah. I'm trying to see where he first mentioned the antiparaplanar. So when you're looking at the chairs, you know, we said equatorial is less energy, right? So when the large group are equatorial, there's less strain. So tert-butyl toxide is a large base. It's a large substituent, right? Tert-butyl, that's 4 carbons. So it being equatorial makes it more stable. And then as far as looking at our antiparaplanar, so this is our alpha carbon here, because it's connected to our chlorine, which is the leaving group, which means this is a beta carbon and this is a beta carbon, right? This is axial. So our para is the ones that are like right next to it, right? Antiparaplanar though, so we don't want it to be on the same plane as the chlorine. This is going down, this is also going down. So this is just too close to the chlorine. Right, it causes steric hindrance. If the base were to try to go after this one, you know, it's going to be bumping into the chlorine. This is axial, so these are going to be our antiparaplanar ones. They're as far away from the tert-butyl, or chlorine, sorry, as possible. And then this is just more stable overall because our tert-butyl is equatorial. So that's kind of what we talked about. I feel like there was an example. This is why, so it's unfavored. So in this example, we went after the syn paraplanar hydrogen. So this is our bromine. This is our hydrogen, right? It's the same. This is like cis, I guess is another way you could look at it. And it ends up like the hydrogen's going, this is the beta carbon, alpha carbon because of the bromine. So we're going after the beta carbon's hydrogen, but this is not antiparaplanar. It's syn paraplanar. base comes in, right? Everything is happening on the same side of the molecule. Like, it's so busy up here versus there's nothing going on down at the bottom, right? It's just not very favorable. Chemicals don't like to react like that. They're, they want their space to do their thing. And so that's why this is going to be less favored. I don't know if he mentioned to you guys the trans 1,2 diaxial. This is just another part of the regioselectivity and our antiparaplanarness. If you guys have any more questions on that, we can talk about it. I'm hoping that that the practice quiz is going to have examples like that, so I can just go over it there, because I'm not the best at coming up with my own examples. Okay, so let's just go through the practice quiz, and then that way, hopefully it'll pop up on its own, and I can explain it there, instead of just trying to come up with it on my own, because I'm not very good at that. Okay. All right, so we just talked about the stability, ranking it from most to least stable. So let's look at them one at a time. The carbons on the double bond are here, right? And then we'll mark the carbons they're connected to with blue. So this one's connected to 1, 2. So this is di substituted. Carbons on the double bond are here and here. This one's connected to 1. This carbon is connected to 2. So we're tri-substituted. Carbons on the double bond are here and here. It's only connected to 1 carbon. Right? So this is a mono. And then carbons here and here, connected to 1, 2. This is another di. Okay. So what's the most stable? Tri-substituted, right? 3 carbons. It's connected to more. So we know that 2 is the most stable, and it wants us to rank them from least to most. So most stable is on the right here, right? Going to the right. So that means we can eliminate this one and this one, because 3 monosubstituted definitely ain't the most stable. We're looking for 2 to be all the way on the right. Okay. Now, we've got 2 di-substituted that are going to be the next stable, right? What kind of conformation is this? It's cis. What kind of conformation is this? Trans. And as we've talked about before, trans is more stable than cis. It's just a little bit more balanced. Okay, so that means 1 should be next. This one has 4 next. 4 is not more stable. So our answer is going to be C. Okay, makes sense? Hopefully. Okay, appropriate base below. So we've got 1, 2, and then 3. So this is a tertiary alkyl halide, right? The carbon here is connected to 3. So this means that it could either be E1 or E2, right? So we talked about bases. Everything we're looking at here, totally forgot to include that one. NaH, strong base. Okay, so this is a strong base. Strong, 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 right? They're all on the list of strong bases we did. Okay, if they're all strong bases, right? this one wasn't on our list. So that means these are all the same in the sense that they're strong bases. That makes it an E2 reaction. Strong, this is also what I should have included, is that an E2, strong, non-bulky, right? If it's a huge bulky base, meaning it seems like it's large, like this is a large compound. Look, it's got 3 methyl groups. If we were to draw it, it'd be oxygen connected to a carbon. This carbon has 3, right? Negative, and then we've got our K positive. Right? So this is bulky. Like, look at all these substituents just like hanging off. Imagine that trying to bond with something versus this is Na, got oxygen, CH3. That's all. Not bulky. Very small. This is going to be the section that reacts, right? Let's look at this one. Na positive. And then, our H. This is going to be the part that reacts anyways. It's going to get snatched. K positive. Oxygen. Hydrogen. These are very small in comparison. Oh, where am I going? In comparison to this, right? This looks kind of bulky. So if E2 happens simultaneously, it would need a non-bulky base. It would need something small that can get in there and react fast. E1, however, it's a multi-step reaction because our carbocation is fairly stable on its own, so the base can take its time getting in there. It's fine if it's big, it's got space because the leaving group is already gone, right? So that's one way to think about it. And then, let's look at this. It's only a di substituted, right? It's not as stable as it possibly could have been. Because this is an alpha carbon, or not alpha. This is the alpha carbon. These are beta carbons. Right? So if this hydrogen was the one who bonded and made the double bond there, it would have been, more substituted because it would have had this 1, 2, 3, right? It would have been tri-substituted. So there was a possibility of creating a more substituted double bond than this one. And E2 also forms the most substituted, most stable. So everything we're looking at here is pointing to the fact that this is just an E1 reaction. And if it's E1, the base that would work best with it is this one, D. So all of these, A, B, and C, have something in common. They're strong, non-bulky bases, which if this was E2, any one of them would have worked. The only one that's different in our answer choices is this one, because it is a bulky, not very strong base. Okay, now let's look here. So, I've got what kind of base? This is a strong base, right? Strong base, E2 reaction. Okay? So, E2, based on Zaitsev's rule, don't remember how to spell that. It's going to create the most substituted alkene, right? Okay, so now let's look at that. So where's our alpha carbon? I'll mark it in red. Here, because it's connected to the leaving group, right? So our beta carbons are just the carbons connected to the alpha carbon. So all these are beta carbons. This one has a hydrogen. This has 3 hydrogens. This one has 2 hydrogens. Okay. The best hydrogen to take in an E2 reaction, right? The farthest one away that will create the most substituted bond, right? It's going to be this one. Because then, as our OCH3 takes this is going to throw it here. We've got a double bond forming there, right? We're going to end up creating this product because our double bond is here, right? None of these have the double bond there in the middle. This is a this is tetra substituted. This is as most stable as it can possibly get, ever. If we took off, hypothetically, if we took off like this hydrogen, it would have, or one of these hydrogens, any of these three, it would have thrown the bond here. The double bond would have been attached to this carbon, which would have been this. This is only di-substituted. That's not as stable as it can get. Then, if we were to take a hydrogen here from one of these from this carbon, it would have been throwing the bond here to this one, which would have been this example, the double bond here. In no way, shape, or form are we ever going to create this anyways, because the double bond did not even form between the beta and the alpha carbon, which it has to. Obi, what did you do, bro? Sorry about that, buddy. Guys, I just tried to put Obi on his cat bed, and I accidentally knocked it over, and the cat bed just fell on top of him. Anyways, so I hope that makes sense. We were never going to form this product anyways, because it didn't even form a double bond between the alpha and beta carbon, which is a must. Okay, this one. Big old bulky base, right? Look at that. We've got oxygen, because it's not actually bonded to this, connected to a carbon that has 3 methyls, right? This is what we're talking about, a bulky base. And if it's bulky, that means it's not E2, it's E1. And E1 is not necessarily trying to form the most stable alkene. So let's look at it. Where's our alpha carbon? Here. Where are our beta carbons? Here. Right? This has hydrogen, hydrogen. This one only has 1, because it already has 3 bonds. Okay. Now, this is going to pop off. That's our leaving group. Which hydrogen do you think this base can get to? This has a lot of steric hindrance, right? This hydrogen has a lot of steric hindrance. It's got to try to squeeze through with this, big old ring next to it, versus these are kind of just out there, right? So I wager that this is going to be the one that gets taken off, right? So we can actually reach in here, get our O- connected to carbon. There are 3 methyls. Take this one. This hydrogen will pop the bond there. Then we've got double bond forming here. This could never happen. Our alpha carbon is here. The double bond, I'm going to write that out because we keep getting examples like that. The double bond has to form between the beta carbon or a beta carbon. I don't need to capitalize that. Between a beta carbon and the alpha carbon. Has to. That's how this works, right? Because it's the alpha carbon that is gaining the charge. So it didn't gain a hydrogen, and it didn't get a double bond, so now it's just still unhappy. So A was not going to happen. B is not going to happen because it's a bulky base, and there's too much steric hindrance to take off this hydrogen here, right? There's too much steric hindrance. We can't get that one. So B wasn't going to happen. C is our answer because it looks exactly like what we just drew. And D, again, not possible because our alpha carbon's over here. So it didn't even form a double bond between an alpha and a beta carbon. So D can't happen. C, perfect. Did we check this one? Okay, good. It's B. Okay, which one would undergo the fastest elimination reaction? So let's look at what has... Okay, let's just look at the terms of an elimination reaction, right? So this is the alpha carbon. Where are beta carbons? Here and here, right? Okay, let's look at our beta carbons. Do any of them even have a hydrogen to react? This one has 2 methyl groups. So this one has no hydrogens, or 3 methyl groups, sorry. This one also cannot react. No hydrogens. Okay, that one's eliminated. This one, if we look at it, this is our alpha carbon. No beta carbons. How can we react? Right? Can't react. No beta carbons, which means no beta carbon hydrogen. So this one's also gone. This one, where's our alpha carbon? Good. Beta carbon, beta carbon. So this beta carbon has 1, 2, 3, 4 bonds. This one can't react, but this one still has 2 hydrogens, right? So that's possible. This one, alpha carbon here, beta carbon here. We only have 1 beta carbon. This one has 1, 2, 3, 4 bonds, no hydrogens. Also cannot react. So really our only answer choice left is C, because it's the only one that even has beta carbons to react. Okay. Which of the following bromides would undergo an E2... Oh, wait, let's check. C. Okay, good. Which of the following bromides could undergo an E2 type elimination reaction? Okay, so let's look at them again. This one, this is the alpha carbon. Technically, it's connected to the bromine. It already has a double bond. So that can't work, right? This one, alpha carbon, beta carbon, beta carbon. This one has 1, 2, 3 bonds, so it still has a hydrogen. This one has 1, 2, 3 bonds, still has a hydrogen. Okay, so though this is technically an alpha carbon that can react, look how much steric hindrance there is all around it. Like, to get this hydrogen, you know, it's already trapped between so many things and it's in a ring. This one is also trapped between so much going on. So we'll leave that as an option. However, it's not really looking great for it. Like, there's just a lot going on in this area that it would be really hard to react. Let's look at this one. We've got alpha carbon here, beta carbon, beta carbon. These beta carbons each have 2 hydrogens. Right? Cool. This one looks perfect. You know, they're antiparaplanar. This bromine's all the way up here. These are really far down, right? So I'm thinking C is going to be our best bet. But let's look at D. Alpha carbon, beta carbon, beta carbon. This has 1, 2, 3, 4 bonds. No hydrogens to react. 1, 2, 3, 4 bonds. No hydrogens to react. So D's not it. So the only ones that could possibly react would be... Oh my god. Yeah, you dummy. That's why you just fell. Sorry about that. This one is just not very much steric hindrance. Like, look how open and free it is. This has, like, so much going on. Like, it's trapped between methyls and things like that. So I'm going to go with C. Oh, good. Right answer. Okay. Which one would undergo an E1 elimination reaction? So let's look. We've got alpha carbon, beta carbon. This has one hydrogen, sorry. This one also only has one hydrogen. Okay, so it's possible. Alpha carbon, beta carbon. Oop. This one has 1, 2. This one has 1, 2. 1, 2, 3. So it can react. Alpha carbon. Ooh, double bond on our alpha carbon. Gone. We're forming a double bond, so that's not going to work. Then we've got alpha carbon, beta carbon. 1 hydrogen. Okay. So let's think about what E1 is, right? It's a multi-step reaction, right? So we need a stable carbocation, meaning it needs to be tertiary or secondary, preferably tertiary, right? Remember that? It's going to be the most stable carbocation. So let's look. Out of the two, this one is di, right? We look at our alpha carbon here, and it's got 2 on it. So this is a di. Let's look at the next one. This is our alpha carbon. It has 3 carbons attached to it. So this is tri-substituted. So this is already more stable than this one. This one couldn't work at all. And then this one only has 1. It's mono-substituted. Once this leaves, this carbon is not going to be happy at all. It's going to be a monocarbocation, or is it methyl carbocation? I forget the name of it. Anyways, it's only got 1 carbon, right? Like, it's not happy. That's not stable at all. So our best choice is going to be B, because it's going to leave us with the most stable carbocation intermediate. Okay, which of the following alkyl bromides would undergo a relatively fast E2 elimination type? Okay, so when we look at this is what we were talking about with the chairs, right? Let's make a chair of this. 1, 2, 3, 4, 5, 6. We'll label this 1, 2, 3, 4, 5, 6. Okay. So we said bold was up, dashed was down. Okay. So we've got 1, 2, our tert butyl. Let's do a ring flip, because our tert butyl is axial, and that is not very stable. Wait. Guys, why can't I draw these right now? Okay. 1 was the utmost carbon, now it's down. 2, 3, 4, 5, 6. So 1 up, tert butyl down. So our tert butyl's here. See, that's still not very stable. Now it's equatorial, but now both of them are equatorial. Our bromine, and bromine needs to be, axial. Otherwise, it won't be antiparaplanar to the hydrogens. So this isn't going to work very well. Let's look at this one. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, bromine, we said dashed was down, down, down. 4, bold was up. So our tert-butyl's up. 4, up, tert-butyl. So on this ring structure, I'm going to spread them out a little bit. Right? This ring structure, not very stable, right? We've got our largest substituent and it's axial. It's not very stable. And our bromine is still axial. Right? That one's not very stable because of this. This one, though this part is stable, we want bromine to be axial. So that way the hydrogen can be antiparaplanar to the to it, right? So this also isn't going to work. So B's not going to work. Let's try again. And yes, it's a pain. You have to draw out the chair structures unless you figure out a way to just know it. I don't. Okay, let's try this one. We said up, up. So 1, 2, 3, 4, 6. 1 is up, 4, up. 1, up, 4, up. Okay, so this one, not stable. This is our tert-butyl group. It's axial. We don't like that. And our bromine is equatorial. We also don't like that. However, our tert-butyl group on this one is equatorial. And our bromine is axial. So we like this. That's a good chair structure right there. Let's check this last one. One, two, oh, numbering that, not good. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so our bromine, up, up, bold wedge, up, bromine, up, bromine. Tert-butyl on 3 is going to be also up. Not good. Up. So again, this we like. It's equatorial. Oh, Lord. Equatorial, it's stable. We don't like that this is equatorial. We want it to be axial. This is axial, which is good. However, this is also axial. We don't like that. So we don't like D either. So our best answer choice is going to be C. Cool. Hope you guys understood that. All right, cool. What did we say about this? We got 2 equivalents. What are we creating? Because this is a base, right? Base. We got 2 equivalents of base. What are we creating? An internal alkyne. Okay, so now let's look. This is an alkene. Wrong. Alkene. Wrong. Nothing. We did nothing. We just somehow ripped the bromines off and did nothing. Doesn't make any sense. Boom! Internal alkyne. Cool. So I hope that made sense. I hope I covered everything thoroughly for you guys. If not, send me any questions that you guys have. I'll be happy to go over it with you. Good luck on your guys'